Okay, good morning. I don't know how to emphasize the importance of the transmission line, and particularly what we are going to discuss today. Uh, Let me put this way: it takes more than 40% of the final exam mark. Okay. Let's first quickly review the key point, what we had yesterday, to describe we call a general transmission line properties. Okay, the general property we have for transmission line is derived from this circuit model. Okay, this circuit model describe a very short, how short it is, delta Z. Okay, for such a short transmission line, what is the basic properties, the electrical property, right? Then we apply KVL and the KCL, right? We can generate two differential equations, first order, this and this, right? So if you don't remember anything, okay, if you couldn't remember anything, okay, by the way, all the required formula equations about the transmission line, I don't provide in final exam, because either you remember it or you derive it, okay? And other things, okay, I provide a complete page of equations, okay? But about transmission line equation, you have to remember or you have to derive. How to derive? Starting from this circuit model. Okay, this circuit model is unstable, you see, for series connection, we have inductors, right? We have inductor has a loss, then between the conductor and the ground, we have a capacitance, okay? And then we also have a substrate loss, okay? From this circuit model plus KVL, KCL equation, we can derive these two differential equations, okay? The two differential equations in time harmonic case in using phasor properties, okay? So we know the directivity with time equivalent to you multiply by j omega, right? So these two equations become this, okay? Becomes this. So this is straightforward, right? Then this equation, you take another directivity with respect to that, okay? We can generate two wave equations, one for voltage, one for current, okay? And in the same time, okay, these two wave equation already tells us complete basic property of the transmission line. That determined by the circuit model, okay? Which two basic properties? One is, I have to change the color. So this is very important, is one is propagation constant, okay? Because the solution of either voltage or current is an ordinary second order differential equation. Then its a solution we know contains two parts. One is exponential term minus gamma z. One is plus gamma z. Okay, so these two solution form multiplied by arbitrary constant. Okay, arbitrary constant. this is a constant. Okay, this is a constant, right? And if you're not sure this or this a solution of this wave equation, easy to substitute them back. Okay, substitute takes less than 10 seconds. You can convince yourself. Okay, if you don't do it, if you're reluctant to do it, that's fine, right? But remember them. Okay, so from circuit model to this solution really will take less than 1 minute. Okay, takes less than 1 minute. Now we know, okay, any of this solution, for example, this, okay, for example, this is, we know gamma is alpha plus J beta, right? So this is okay. So the first term means how the signal attenuate when the medium is full of, is a lossy medium, right? How it attenuate when increase that, right? The second term is when you increase that, how the phase change. So this is exactly the same as a Planck wave. So I don't like to spend time, okay? Right? So clearly, this term means wave propagate in positive z direction. Okay, then this is wave in minus z direction. Okay, so far we don't have any problem. Okay, now again, if you substitute one of the solutions, if you substitute this into differential equation, okay, into differential equation together with this, okay, together with this, then you can find this ratio, okay? You can find this ratio equal to this, okay? So this is still from differential equation. If you substitute the wave propagating in minus z direction into this general equation, okay, you got this relation, okay, you got this relation. So therefore, we have found another important property, okay, important property. So far we have two important property, 1 and 2, okay, to describe a transmission line. Electrically, we only need to have these two parameters, okay? With these two parameters, all the electrical properties about the transmission line is given, okay? So this property, one is gamma, one is we call characteristic impedance. The propagation constant okay, and the characteristic impedance. Okay, we only need to have these two. Okay, the basic electrical property. Okay, of transmission line. We only have these two. Okay, we only have these two. And these two all depend on the basic property of the circuit model R, L, C, and G, right? And those are capacitor, inductance, resistance, and conductance per unit length. All right. Now we are ready to apply the basic property for communication system. Okay, is there the high frequency RF circuit? Okay, let me hold. We only have 32 count. All right, so I hope at least we have a 32 student pass our final exam. Right? Okay. Now we discuss a practical situation. What a practical situation in applications? We have a load. This load could be antenna, or could be RFIC. Okay, could be anything. Okay, any high frequency stuff. Okay, any high frequency, high speed circuit. So we call this load. Okay, we call load. So load is put on the one end of the transmission line. So this transmission line, we have a total length. We have a total length L. This length makes difference. This is different from what we call the ordinary electrical circuit. Say for ordinary electrical circuit, okay, for ordinary circuit, if I have resistor, then this is the node. I also draw very long. This is R2. Okay. This whole thing, this exactly equal to right? So if this is a node A, this is node A, right? So the length is a really doesn't matter. We never care. We never care, right? But to transmission line, by the way, this length doesn't matter how long. Even this last 1 kilometer doesn't make difference. Doesn't make difference. You see, the reason is if you calculate what is the signal, the wavelength, okay? Let's say the wavelength. And in the discussion of Planck wave, I gave you a simple formula, okay? The wavelength in terms of millimeter, okay, is frequency gigahertz, okay? This is a millimeter, this is millimeter. But if this is, say, if this is in meter, so that means I multiply 1,000 times. Sorry. Okay, 1,000 times. Then this also multiplied by 1,000 times. Okay, so if this is a frequency is a gigahertz, so this become, this is a frequency megahertz times 1,000. Okay, so that means if frequency in megahertz, this is in meter. Wavelength is in meter. Okay, now let's say if our frequency in Hong Kong, the outlet, okay, the power frequency, the AC is 50 hertz, right? 50 hertz. 50 hertz is how many megahertz? Is 50 times 6 megahertz. Okay, right? So let's say, what is the wavelength for the power, for the voltage current in the power line we have is 300 divided by 50 and meter. Okay, so okay, that is a 6,000 kilometer wavelength. Okay, so if I use 1 kilometer long, how many wavelengths it is? This is 1,000 or one if one over 6,000 wavelengths, okay, for 1 kilometer, okay, at 50 hertz. All right, so really the physical length is so small compared to wavelength, so that's why we can ignore. Okay, but to transmission line is different. Okay, we will see. Okay, for transmission line, the length is all in fractional of wavelength, so that matters. Okay, we'll see why it is matter. Now go back to the basic property of the transmission line. Down the transmission line, we know we have two possible. We have coefficient we need to determine. Okay, the coefficient one is this voltage. Let's talk about the voltage. Okay, the voltage, if we know the voltage, we know the current. Why is this? Because if we know the voltage, this is a magnitude for traveling wave, right? Then if we divide by the magnitude of current also travel in the same direction, this equal to the characteristic impedance, right? So that's why we only need to pay attention to one constant. We don't need to worry two right now, right? Okay. Now let's say why sketch a transmission line. I don't use this thin wire anymore. This is thin wire, right? I use very thick. Okay, how thick it is? I use thick wire to indicate this is a transmission line. Okay, this is transmission line. Okay, then I can use very thin wire to indicate this is ordinary. Say, I use very thin wire to indicate this is ordinary circuit. So that means the length does not matter. Okay, does not matter. Now you see the difference. Okay, now you see the difference. Now, okay, let's go back to original because I think this the original drawing is thick enough to distinguish the transmission line and the ordinary circuit line. Right? Now, as I put load on one side, okay? Then I put source on the other side, okay? This source could be transmitted. Okay, this is transmitter. So we have signal generator, even though we only generate it one frequency. Okay, we only consider it one frequency. Let's assume this generator only generates one frequency. Okay, this generator has an internal impedance any transmitter has internal impedance. So don't surprise, right? Now our task is for giving this, can we determine those two unknowns? Unknown 1, unknown 2, or at least the relationship of these two unknowns. Okay, can we determine them? Okay, we need to determine them, right? So once we determine them, then we can find what is the voltage at any location, okay, or what is the current at any location, right? So we also need to know the impedance looking toward the load at any location. Then you say, hey, this impedance, we already had the impedance for characteristic impedance, okay? What is this impedance? Yes, characteristic impedance is measured using traveling wave, right? You see, this is traveling wave measured, and using this is also traveling wave, right? This is also traveling wave, but the impedance at transmission line at any location is a total wave and a total current. It's not traveling wave, it's a standing wave. Okay, it's a summation of wave travel toward both directions. Okay, so this is what we want to do. Okay, now we recall. Right, recall what we have, right? We have the total voltage at any location is a superposition of positive traveled wave and a negative traveled wave, which is mathematically represented by exponential function, okay, with the propagation constant in general is complex, okay, and then with a magnitude that need to determine that it depend on the boundary condition. What is boundary condition now? Is a load, okay, and also the source, right? But in most of the time, we're not interested in how we build the source. We're only interested in what our load is, okay? And similarly, we have a current, right? Okay, now let's say how to determine them, okay? If you know how to determine them by yourself, okay, then you take another 1 more minute, you can derive all the transmission line equation, okay? Let's see how we derive them. Let's look at, because we measure the Z from here right now, okay? This is it, this is that. We measure it when Z equal to L. That means at the load location, the total voltage over total current must satisfy Ohm's law, okay? Must satisfy Ohm's law. Or we can say the total voltage at the load, mathematically we can represent by two waves add together. This concept we also use in time domain analysis, right? Okay, then we have one equation, okay? And also the current is the load, we can use, represent this by voltage, right? And this is by minus, don't forget minus, by this, okay? So I replace these two current. The reason is let's focus on two unknowns, right, on voltage, because we know these two. Once we know these two unknowns, we know the unknowns on current. Okay, so that is the second equation after we replace them, right? So we don't have any new information. The only information, right? We don't have any new information so far. Okay, this is just specifically means the voltage and the current is the load. From these two equations, it's two equations. We have two unknowns. We can easily find this. Okay, we can easily find this. Right. This takes less than 1 minute. Okay. Then also we know if the load follow Ohm's law, right? Follow Ohm's law, right? So these two equations, then in this case, I replace this by ZL times IL. Okay, this equal to ZL times IL. Okay. You see, not the reason I replace this is because I like to keep the same unknowns, right? Keep some unknown. So I can extract this unknown. All right. I can extract this unknown. Then we already have its infancy. We have infancy of the transmission line equations. Okay. It is almost there. It is almost there. Okay. We have this. We have this. We have this. Okay. Let's go one more step. Okay. One more step. I have 3 minutes before you say. So Arjun asked me to hand over to him, and he will conduct the cost evaluation. Okay. And also in the recess time. Okay. After you fill in the form, we resume at 10:30, and then during this recess time, I ask every one of you to repeat this derivation by yourself. Okay, it greatly helps if you close your eyes. If you can repeat it, okay, then you don't need to remember all those formulas. Okay, then those formulas you will use that take 40% of score in final exam. Okay, I won't supply you. Okay, now when we look at this equation, we see something is not convenient. Okay, what is not convenient is we always use L minus Z, L minus Z, L minus Z. Okay, you will find out how it comes from when you derive it. Okay, so L minus Z means we have a total length of L. Then we have this length is Z. The L minus Z is this. This is L minus Z. Right? L minus Z is this distance. Okay. This is L minus. Oh, sorry. L minus Z. L minus Z is this distance, right? Okay, yes, this is that. Okay, now let's do a simple variable replacement. I use Z prime to replace L minus Z. Okay, so the same equation, but I just use Z prime. What is the difference is Z prime is more convenient. Okay, more convenient is we measure the distance away from the load. That means this is Z prime, and this is Z. Okay, you see, so that measure the distance from transmitter. Z prime measures the distance from load, okay, from load. So we think this is more convenient. This is more convenient. So far, let's stop here, okay? We stop here. Then can you repeat this derivation before we resume our class, right? Okay, I hand over this to Ajin, right? So I will come, let's resume our class at 10:30. And then after you fill in the form, repeat my derivation by yourself, okay? So you have sufficient time, you can sufficient time to repeat 10 times, all right? Recording. So anybody got time to derive the formula just now? Can I get any answer? So anybody try? Nobody try. All right. Okay. So if nobody try, do it. Do it after class. Right. Okay. This is we got a basic transmission line equation. Okay. This equation tells us the relation, right? The relation between voltage, current, characteristic impedance, your load impedance, okay, and importantly, the distance from the source, right? For giving Z and gamma, okay, for giving this, right? For giving this. So that's supposed is exactly what we need. We have everything we need, right? But the exponential function forms is not very convenient for us, okay? Not very convenient for some of us, okay? For some of us. Then we can write this like, we can rewrite this, okay? We can rewrite this in the way that if anything ZL related, right? We can write in this way, right? So this reminds us, hey, we use a definition of hyperbolic function, okay? Hyperbolic function. Hyperbolic function deal with such exponential functions, okay? So therefore if we divide by 2, multiply by 2, divided by 2, multiply by 2, right? Then we can replace this by Cauchy and such functions, okay? In this way, we have another form of transmission line equation. So basically it's the same thing, right? So this, we can come to this, right? Now, this is already in the form of usable form, okay, usable form. And later on, you see, let's simplify this to a lossless case, okay? Let's simplify this to lossless case later on. But in the meantime, let's deal with these hyperbolic functions, okay? First, you say, what is use? Okay, what is use of this tool? First, let's find the ratio of total voltage over total current. Okay, let's find what is this. Because as electrical engineers, we always deal with impedance, right? Always deal with impedance, and later on, we will deal with impedance matching, right? Why we do impedance matching? Because we need to transfer most of the energy to the load, right? And then we don't want to have too much reflection. Then we need to define impedance. The impedance is defined at any location down the transmission line. If we can measure the voltage, we can measure the current. Then we take a ratio. Okay, we take a ratio. Then we define this. This is defined as our impedance. Okay, but this impedance is looking toward load. Why we say it's looking toward the load? Because we measure the distance from the load, right? We measure distance from the load. You cannot tell me this is looking toward the source, right? Because even you don't know what is distance to the source, right? If you couldn't describe what is distance to the source, what is the point? You said, oh, I'm looking at the source. If you look at the source, you must tell what is distance away from the source, right? Now we only know the distance from the load, okay? The distance to the load is Z prime, right? So once you take ratio of this, then this current cancel, right? Because that is a common term. This current as the load cancel, okay? Then this is only determined by the essential characteristic impedance, characteristic properties of transmission line, which is a characteristic impedance, propagation constant, okay, and also depend on your load and the distance to the load, right? That's all we need, okay? From this, we can determine what is impedance. This may be the first time to most of us say, hey, is impedance change with location. Impedance change with location. Okay, because this is the concept only for high frequency, only for transmission line problem. For ordinary circuit, we never had such problems. The impedance, if we have two nodes, we have a conducting wire, and then the impedance, if you're looking from this or looking from here, something, right? Something. Right? Something. So in ordinary circuit, we don't have this problem. But in RF, in microwave circuit, then the impedance at different location is different, okay? And of course, it is proportional to the characteristic impedance, okay? Now, okay, now if we have, where's our diagram? Okay. if we're looking toward load at the source, okay, we looking toward at the source. If we know what is impedance, this location is Z prime equal to a total length, right? So total length, okay. Then we say this problem become, oh, we have a transmitter, internal impedance, okay. Then everything here, okay, everything here is equivalent to Z, okay, Z prime equal to M. Okay, now in this circumstance, we can use the ordinary circuit theory, okay, because we don't have, oh, if you think this is too thick, I use thin wire to describe this become ordinary circuit, okay? We don't have transmission line, okay? We used to use a thicker wire to indicate this is transmission line, okay? Now you can use KVL, okay? You can use KCL, or if you like to find the current, okay, from the source, okay? If you know the source, then you can use everything using ordinary circuit theory, okay? Right, ordinary circuit theory. So, but however, before you're using ordinary circuit theory, okay, you have to apply transmission line theory first to deal with microwave circuit, okay? Now, this is a equivalent circuit I just mentioned, okay? Then you see, because we know the hyperbolic tangent function h equal to this, right? So we divide Cauchy function on numerator and the denominator in the same time. So this we can obtain, right? So this is just looks more compact. We didn't bring in any new information, okay? Not any new information. And then sometimes people also like to call, hey, this is transmission line. This is transmission line theory. Okay, this is transmission line theory. Okay, if this is I should say this is part of the transmission line theory. All right, because we take a ratio of voltage over current. Right? We define impedance. Right, this is V divided by I equal to this. Right, and on the lossless case, okay, lossless case, okay, gamma suppose is equal to alpha G beta, then alpha equal to 0 for lossless case, okay? Then we have G beta, okay? Under this case, okay, then the characteristic impedance is also a real because this, okay? You can refer to our general expression why this is real, okay? For lossless case, and R equal to 0, okay, and G equal to 0, okay? G equal to 0. Oh, sorry, G equal to infinity. I almost make a mistake. Okay, G equal to infinity. All right, so in this case, this function simply becomes this, right? This is high school stuff, so we don't repeat. So this looks more what? More compact. Not this we lay very important foundation for our future discussion. Okay, let's move on, right? We still talk about transmission line of finite length. Okay, we repeat this formula we just had. Okay, for lossless case. Let's discuss some special cases. Okay, let's discuss some special cases. Oh, by the way, you see this. Okay, we talk about lossless case. We draw the transmission line, right? We draw the transmission line. We use a thicker. Well, then we use a thin well. Okay, and then actually on this side, we really don't care, right? Why we care how we build the transmitter, right? Because everything has nothing to do, if you look at this formula, nothing to do with transmitter, right? Nothing to do with transmitter. So the same as when you use a mobile phone, do you care how the signal is generated when you hold the phone? No, right? And then we may care, you see, how we make antenna works better, right? And but we never worry, you see, how we generate signal. So in this discussion, we don't care about source. Okay, let me put here. We have a source on this side, okay? And then I don't care how it is connected, okay? And how far it is from the load is also not our concern, right? Now, in this case, let's talk about, this is a lossless case, so we have R0, okay? We have a beta. This is the basic property of the transmission line, okay? Now, let's say we look at a certain location, this location with load, distance is L, okay? Distance is L. This is exactly what this says, okay? Now, let's say, once the load become infinity, what is the case of the load becoming infinity is the current is zero, right? The current goes through the load is zero. What is this case? Is an open circuit, okay? So we have an open circuit case. Once this load goes to infinity, this goes to infinity, this goes to infinity, right? So we really don't care about these two, right? So we just don't care about these two. So this infinity over infinity, because these two are not, compared to these larger two terms, is negligible, okay? It's negligible. See, if this is a 10 power of 6, and this is only power of 1 or power of 0, right? Or power of 1, say. So it's negligible, so, right? So we don't care about these two. So that means we really don't care these two. So because this is so large, so this, we can cancel each other. We can cancel each other. As a result, we have impedance. Result is this, okay? Because the minus sign, so 1 over GA equal to minus G, okay? I use this, all right? So if you look at this function, that behavior like this, once the beta L, when beta L equal to pi, okay? Equal to pi. So what that means is beta L equal to pi. So beta L equal to 2 pi over lambda, right? Equal to pi, okay? Then the L equal to lambda over 2, right? So that means once this equal to pi, this goes to 0 and the impedance goes to infinity, okay? That goes to infinity, that goes to infinity. So once this beta L, 1 beta L equal to 1 beta L equal to pi over 2, okay? So 1 beta tangent pi over 2, tangent pi over 2. What's that equal to? This equal to infinity, right? So that means when this goes to infinity, so that means L equal to lambda divided by 4, right? So the impedance goes to 0 because this goes to infinity, so this goes to 0. So at a different location or different frequency, it depends on what you're talking about, right? Because we have a beta L, we can either change beta or we can change L. Fix L, we can change beta, or we can change wavelengths, or we fix the wavelengths, we can change L, right? We can change L. So that means, let's say we fix the frequency. Okay, let's say we fix the frequency. That means at a different location. If this location is lambda over 4, the impedance once it's open circuit, okay, once this is open circuit, once the open circuit, what do you say? Okay, what do you say is the impedance? What do you say is this equal to 0? Okay, but if you move away, okay, if you move away to observe the impedance, if you're looking from this side, okay, this is another quarter wavelength, okay, another quarter wavelength, then this impedance, according to this, equal to infinity, okay, equal to infinity, right? So the different value, the different location will have different impedance, okay? So this is for open circuit, this is for open circuit. Very special case is, okay, what happened if I observe this is very close, very close, okay, very close to the open circuit. What is this? What is this? Okay, very close. So we can use Taylor series expansion. Okay, we use the Taylor series expansion is when beta L is very smaller than 1. Okay, when x is very smaller than 1, then tangent x approximately equal to x. Okay, equal to x. So we use this approximation. Okay, then we replace tangent beta L by beta L. Okay, by beta L. Then we know for lossless case, and z R0 equal to this. Okay, and beta equal to omega L over C. Why is beta to omega IROC because beta equal to omega phase velocity, omega divided by phase velocity. We know phase velocity is L over C, so right? So this means, okay, beta. So this is interesting. What's that equal to? This equal to okay, because this capital C is being used. Capital C is capacitance per unit length, okay? But we know the total length, this distance is, even though it's very small, but it is L, okay? It is L, right? The length is L. So the beta L is very, very smaller than 1, okay? So the total capacitance, so the C prime is capacitance per unit length multiplied by the total length, L. This is total capacitance. Is this look familiar? This equation is, we suppose we learned this in circuit theory, right? If for given capacitance, what is impedance? What is impedance? The impedance equal to 1 over J omega C, right? If this is, okay. So what that means is, if we have open circuit transmission line, but very, very short, that equivalent to a capacitance, okay? Equivalent to a capacitance. This is a very popular way we realize a capacitance. We realize a capacitance in RF radio frequency circuit design, okay? We don't need to find a capacitor. But by the way, for high frequency capacitor, it's very different from low frequency capacitor, okay? It's much more expensive and much more sophisticated, okay? But we don't need to use capacitor, a real capacitor, we just use capacitor. We just use an open circuit transmission line, okay? So this is the first case for open circuit. For short circuit, let's go quick, okay? For short circuit, basically, we connect this, okay? We connect this. For short circuit, okay, let me put here. For short circuit, then this general transmission line equation, okay, we set this equal to 0, this equal to 0, and R0 canceled, okay? So we have this. We have this, okay? So this, you can say the property is almost reverse of open circuit. Everything is a reverse, right? Everything is a reverse, okay? But everything reverse except this, because characteristic impedance is always our reference, okay? Is proportional to the total impedance, no matter open circuit or short circuit, all right? But so in this case, of course, when length equal to 0, this is 0, okay? When length is quarter wavelength, okay, this goes to infinity, and then is once it's a half wavelength, becomes short circuit again, right? And also, you see, look at the open circuit case. When it is 0, open circuit, right? Infinity. When it's a half wavelength, it's also open circuit, infinity. And then that open circuit repeat every half wavelength. And also the open circuit or short circuit for short circuited transmission line also repeated every half wavelength, This is because of the trigonometry function. It has it's a period of 2 pi, right? Also, for a very short length, short circuit transmission line, this approximation, okay, this equal to beta L, okay, still valid, right? So then we can find the impedance equal to this, or this is J omega L E prime. L prime is a total inductance because unit inductance multiplied by total length L, right? So that means another way we realize inductor in our circuit is using a very short length short circuit transmission line. Okay. Interesting things. Let's look at this diagram. Okay. From this diagram, we can see from short circuit to open circuit, how long it takes, quarter wavelength. Then from open circuit to short circuit, also another quarter wavelength, right? So that means the property reverse every quarter wavelength, same as this transmission line. From here to here, quarter wavelength, this is another quarter wavelength. So that means for quarter wavelength along transmission line, okay, we have this relation. This is easily derived from property of trigonometric functions, okay? So that means impedance reverse, okay, reverse multiplied by this square, okay? Multiplied by this square, which is characteristic impedance, okay? But if divide by ZL, I define this, I use small letter. This is called normalized impedance. Okay, so what is equal to 1 over ZL divided by 0, right? So this equal to ZL. Okay, so that means ZI equal to 1 over ZL. For normalized impedance, normalized to whom? Normalized to characteristic impedance. It is completely reverse, okay? Reverse, every quarter wavelength is a reverse. Open become short, short become open, okay? Resistor still resistor, but different value, okay? So for half wavelengths, is a repeat, okay? We already see this phenomenon, okay? So this is a very important property. This is a very important property. Also from this property, we can say from open and short circuit, okay, then if we can measure it, okay, if we can measure the open circuit and short circuit impedance, we can do some simple manipulation. We can determine what is the characteristic impedance and the propagation constant. But nobody uses this method to measure them, okay? This is a very ideal method, okay? Now, let's go back to look at the property of the voltage and the current, okay? Because voltage and the current somehow much easier to measure, okay? Much easier to measure the voltage than measure impedance. You can think about, to get impedance, you must know the voltage and the current, right? You need to have two things. And also both must be very accurate, refer to the same location. So this is not that straightforward, okay? But however, if I only measure the voltage, we have many ways we can measure voltage, okay? We can have many ways we can measure voltage. So let's recall the transmission line equation for voltage, okay? Which is, this is something I asked you to derive in the recess time. Okay. The recess time. Not, let's take a close look of this. The sum equation, right? Sum equation, the voltage, sum equation. This is constant. This has nothing to do with distance. I take it out. So once I take it out, the second term, I have to divide this, right? Okay. Then this is not new, right? This is not new. This is something. Oh, let's use sec. Huh? This is something, okay. This is something, the reflection coefficient. We have to repeat this 100 times, right? So the reflection coefficient is what you see and measure the difference to yourself, okay? And then divide yourself and what do you see, right? This is a reflection coefficient for both plane wave and transmission line for digital circuit, right? We use this the reflection coefficient 100 times, okay? Now, if you have a reflection coefficient it load, okay? Now, let's say, what is the reflection coefficient if I observe this plane, okay? So let's assume this distance is Z prime. What is this? What is this? Okay. What is this? This we already have. What is this? Okay. Then let's say we have a wave, when the wave travel this distance, if we have a wave, the magnitude equal to 1, okay, then the traveling wave is minus J beta Z prime. Let's say this location is Z prime. Oh, yes, this is Z prime. I already put it. Okay, so this is the one way. Once the wave is 1 here, so it arrive here is 1 minus J beta Z prime, right? Okay, so this is a one way. If the wave come back, what is this? This is travel another. So this is original beta Z prime. So it's travel another minus J beta Z prime, right? So that equal to 2 times J beta Z prime. Do you agree? Do you agree? So that means, okay, if you have a wave idea perfect, magnitude equal to 1, okay? So after you travel this distance and this distance back, okay, once you travel, okay, once the wave 1 reach to here, okay, that equal to this. And the reflect wave is This wave we call the V minus, right? Okay, V minus. So this is a V minus at the load. Okay, V minus at the load travel this distance, so that's equal to this. Okay, that equal to this. So having understand this, now we can understand better what is this. Okay, this is nothing. This is just reflection coefficient at Z prime. Okay, it's Z prime. Is that clear? Okay, is that clear? So then, what is this? This is V plus at Z. Okay, then we translate this. We translate this equation. This is Z prime. So this equation is nothing but V plus it's Z prime. Okay, and plus, okay, plus V, the incident wave multiplied by reflection, it's Z prime. Okay, or you can call this is V minus at Z prime. Okay, if I interpret what this voltage is, this is what that is. Okay, this is what that is. Okay, now we understand this part is also a reflection coefficient, and we have 2 times in phase because we bought a round way ticket, right? We have a ticket go and ticket back. Okay, I guess you see when we travel, we all buy a round way ticket, right? In most of the time. All right, then in general, the impedance and the load is complex number. All right, so the reflection coefficient is complex number. That is a complex number. If this is a complex number, we have a magnitude, we have a phase. Okay, we have magnitude and phase. So how to deal with the current? So I leave it to you. Right? I leave it to you. It's just very straightforward. Now we have. Let's go back to look at this voltage. Let's go back to this voltage expression. Okay, voltage expression. Then this voltage, if I take magnitude of voltage, if I only look at magnitude, I know it is a complex number, right? It is a complex number. But if I only look at the magnitude, so that means I have this, right? This magnitude is independent to Z prime, right? Because this magnitude equal to this magnitude, right? So this magnitude equal to 1. This magnitude has nothing to do with location distance. So the magnitude of voltage only depend on this. Only depend on this. Or only depend on the voltage only depend on which is a magnitude, okay, and 1 minus or 1 plus gamma, right? Gamma is a function of location, which is complex. which is complex. So therefore, if I draw a vector diagram, okay, because this is a complex plane, right? So this is complex. So if this is 1, okay, so if this is a gamma, okay, if this is gamma, gamma has a magnitude, and then we have theta, right? Okay, gamma. So then this is 1, right? This is 1. So I put this gamma vector here, right? Because we said vector is independent to represent the vector is independent to where it starts, right? It's because vector only measured by the direction and the magnitude, okay? So this gamma, I move this, do you agree? I can move the gamma here. Do you agree? Okay, if no objection, I remove this. Okay, I remove it. Then what is this vector? This vector is gamma. Okay. This vector is nothing but 1 plus gamma, right? This is 1 plus gamma. Right. So 1 plus gamma, then this vector, you can rotate this vector, okay? You can rotate this vector in 360 degree, right? Okay, rotate it. So you have, once this vector, I mark this vector, okay? When this vector come to here, okay? This is a one extreme case. And once this vector the same length, right? So the same length, okay? So once this vector rotate here, this is my, okay. Oh, sorry. So I'm not rotating this vector. I should rotating this vector because only thing I can do is change the reflection coefficient. If I rotate this vector to here, right? Okay, then this is my 1 minus gamma, or 1 plus gamma. Okay, so if I rotate this to this side, okay, then I can roughly estimate this is come here. So this is my 1, oh, sorry. This is first case, right? So once I rotate this vector, once I rotate this vector to here, this become my 1 plus gamma. right? So 1 plus gamma you have two options. One, you have, one you have a maximum value. One you have a minimum value. This is minimum value. This is maximum value. Okay, right? So that means the voltage you can have maximum value is this equal to 1 plus magnitude of this, and this equal to 1 minus gamma, right? Gamma, okay. You see, because gamma 0 equal to gamma, right? Okay, gamma 0 equal to gamma. So if we take a voltage maximum, take a ratio of voltage maximum over voltage minimum, we define a very, very important parameter we call standing wave ratio. We call standing wave ratio. Okay, S. Standing wave ratio is measured maximum voltage, minimum voltage, which you take a ratio of this, so that basically equal to this. And from this, you can easily obtain this. Okay, so that means if we know standing wave ratio, we know the magnitude of reflection coefficient. Sorry, I spent too much time on this. Okay, so let's. Okay, let's go quickly, take another 3 minutes, okay? So when we measure the absolute value of reflection coefficient, okay, we have two cases, right? If the real part of the load larger than characteristic impedance, okay, then we use this formula because this formula ensures the absolute value is positive, right? Otherwise, we have to change. Okay, we have to change the formula. So therefore, we calculate the absolute value of reflection coefficient depending on if the load is smaller than characteristic impedance, or larger than characteristic impedance, or smaller than this. And consequently, because of this is different, so for different value, standing wave ratio is measured in opposite way, okay, in opposite way. So we must be very careful how to use the load impedance to calculate standing wave ratio. In another word, you say if you make a mistake, it's very easy to identify. The reason is standing wave ratio is always larger than 1, okay? It's always larger or smaller than 1, okay? If you somehow, you get the number is less than 1, of course it's wrong, okay? You have to use the other way, okay? You have to use the other way. So it depends on this, we have different way we describe standing wave ratio, okay? So this is somehow, if the L equal to 0, that means the voltage at the load, okay, voltage at load, then we can measure the voltage if this either the maximum or the minimum. In another word, if the load is real, okay, the voltage either maximum or minimum. This is a very important conclusion, okay? Voltage maximum, voltage minimum only occur when load, when impedance, when Z is real. This is Professor Wu said, okay? Very important, very important. If you don't understand this, go back to digest, okay? But we need to use this conclusion in final exam, okay? Remember, this is what Professor Wu said, okay? It's more important than what Einstein said, okay? Right, so this only happened. Now let's see how to understand impedance. Let me show your attention. Here, we can see you observe here, this is impedance. If you draw a line, any reference location, if you can find impedance Z, this is also load impedance. So that basically you move your load reference position. This is a reference plane. Okay. Reference plane is very important concept in microwave, in RF circuit. If you talk about impedance without referring where is your reference plane, what you say means you didn't say anything, okay? Right, so when we talk about impedance, when we talk about the reflection coefficient, we must refer to where you observe it, okay? Every time you observe it, always look toward load, toward the load, okay? Is that clear? No matter if it's young people or old people like me, right? So look toward the load, okay? And define where you look at them, reference plane. Then the statement you make makes sense, okay? Otherwise, doesn't make sense, all right? So I think I leave rest of the concept to TA, okay, to finish this, all right? Okay, let's stop here today.